My name is Morten Birkved. I'm the chairperson of this PhD defense of Jan-Markus Rodger. You have a long name. You know, I tend to mess it up. Anyway, for the defense, we have a group of examiners sitting up here on the first row. First of all, we have Dr. Ingenieur Tina Detmer, Volkswagen AG in Germany, and Professor Wim de Wulf, KU Leuven, Department of Mechanical Engineering. Last but not least, Associate Professor Stig Jeving Olsen from DTU Management Engineering. Jan, Jan-Markus, you had a supervisor, who is Nikki Bai, sitting here. Everyone's present, it seems. Welcome to all of you, also to Nikki, and welcome to the audience. Today you are defending the PhD thesis Sustainability Assessment in the Highly Automated Manufacturing with a presentation of the same name, I've heard. The topic of the thesis is a holistic approach of integration of the sustainability assessment in manufacturing with focus on highly automated production processes. Correct? Jan-Markus, you did your PhD thesis at DTU Management Engineering, Division of Quantitative Sustainability Assessment. I don't know, have there been any other external supervisors? I'm not informed about that. It's just not evident. I guess it's not the case then. Co-supervisors. We have a co-supervisor, Michael Hauschitz, sitting over there. Not to forget. The sequence of what is about going to happen is that Jan-Markus has 45 minutes to give a presentation. After which we'll have a short break where some of you might leave, others might need to go to the toilet. And if the auditorium has questions, some of you have questions, please come to me. I will then make sure that there's time for you to pose your questions. Each questioner from the audience is maximum given 15 minutes according to the rules here at DTU. What I need to allocate in case the examiners decides that they want to go for 2 minutes or 2 hours and 15 minutes in total, that will not leave much time for the audience to pose questions. So please approach me in the break in case you have questions. Okay? I will now give the word to you, Jan-Markus. Please go ahead.
Thanks a lot, Morten. And I would like to welcome my opponents. And yeah, like Morten said, my presentation will be about sustainability assessment in highly automated manufacturing, introducing life cycle targets in the early phase of production planning. To understand the whole topic and so forth, I would like to give you a small background or history why I actually choose this topic. If we start with global aspects global aspects about sustainability, we always have to think about the increase of population until 2050. So an increase of 3 million people we can actually expect according to the United Nations. And if we talk about sustainability, most of the people know, of course, global warming. And the IPCC actually says, or the Paris Accord says, that we should limit the global warming to 2 degrees Celsius, not to have a kind of catalyst effect. And if we translate these 2 degrees Celsius into a target state, we can say, okay, we can still emit 390 to 940 gigatons of CO2 equivalents until 2050. And of course, we have to consider the change of transportation around the globe. A lot of people are demanding different means of transportation, additional mobility. And if we somehow merge these 3 aspects in this well-known equation from Commoner, it's the iPad equation, we can somehow identify which might be the lever for decreasing the impact to the environment. So, but before that, I would like to explain this. So if we look here at the population, you will have an increase of 3 billion people until 2050. We have the affluence, which describes somehow the prosperity around the globe. That will increase as well, hopefully. And then we have the technology, which is the only lever to at least stabilize the impact to the environment or even reduce the impact to the environment. And if we combine this now to the product which I'm focusing on around this PhD thesis, we can see it actually today how this works. So car companies are trying to introduce electrified cars now to the market, so they're changing their technology. But does it actually reduce the environmental impact by using the electrified cars? So just to remember, over a life cycle, a car emits roughly 38 tons for 200,000 kilometers and 10 years. And if we look now at electrified cars, there will be a shifting from the use phase of the emissions to the manufacturing stage. But how much can we actually emit? That is the question. So which CO2 budget is actually allowed to have a stable or a lower impact to the environment? That's the whole question of my PhD thesis, how we can combine the global aspects, the product, and the manufacturing, and how much CO2 emissions can be assigned to manufacturing. Along this way, the car manufacturers have to solve a lot of challenges, or there's challenges ahead, like stakeholders are asking for cheap production, or politics are asking for the introduction for additional regulations and so forth. And of course, we have to think about the rebound effect as well. So the car companies are always striving for more cars. They want to sell more cars to earn more money. But this means that we have additional emissions during the production. So this is called the rebound effect. And then we have the planning, which is kind of important because we have to plan the production line according to this new CO2 budget. But the car manufacturers are producing a lot of variants now. If you look at the Golf car 20 years ago, there were only 4 different kind of variants, and now there are up to 100 available. And then, of course, the planning should take less time. It's a kind of economical pressure from the stakeholders. So this is the whole background around of my PhD thesis. And now I'm getting into detail and would like to present the agenda. So in the beginning, I will talk about my research approach, then the actual method development. After that, I integrate the method into current assessment methods. Then I will apply it in highly automated manufacturing. So I will generate actually results here. And then at the end, I will finish with the conclusion and recommendations. So let's start with a research approach, which is always quite important in a PhD, to do some research. And yeah, I would like to scope my thesis a little bit. So as I mentioned before, I have dealt with the target states, environmental and economic target states, but I will focus on environmental or CO2 emissions in this presentation. So the first research question I have solved in paper 1, actually, how can sustainability assessed in automotive manufacturing using the concept of target states? So how to implement 390 gigatons into the production planning. The second part is the product life cycle of the car. And it's quite important to implement this new thinking into existing simulation tools, because car manufacturers are using a lot of simulation and trying to speed up the planning process. So I've tried to integrate life cycle assessment into production simulation to avoid actual sub-optimization. So the burden shifting from one stage one life cycle phase to the other stage. And then we have the third part, which is about product and production planning. So I had to understand the production planning process in car manufacturing and how a target state for production can be integrated in the early phase of production planning. And the last question is how I can actually assign these target states to the individual processes in a body-wide production. So what CO2 budget should be assigned to robot XY somewhere in the production line. And after I solved all this or answered all this question, I'm pretty happy that I've developed a sustainability assessment method for automated manufacturing. How I have approached these 4 questions will be the content of this slide. So the first part is the method development, and it's the answer of research question 1. And I started with actually the aim was to have a holistic framework for sustainable manufacturing. And I did a literary review in the beginning, gained a lot of knowledge about how to assess sustainability in manufacturing. Then I talked to the partners in the AREAS project. And the AREAS project is mainly is a EU-funded project which lasts from end of 2013 until 2016. And the idea of the project was to assess technologies in highly automated manufacturing. So it somehow fits pretty well to my PhD thesis. And then I was lucky enough to analyze their manufacturing systems. So I gained additional knowledge. And then I added some sustainability assessment approaches. And at the end, I had a holistic framework. But I will talk about this in detail later on. The second part is the integration in current assessment methods. This method somehow have to be applicable. So I collaborated with the TU Brunswick, and we combined life cycle assessment and manufacturing simulation in this part, and we were able to integrate this into current simulation software. The last part, which is the most interesting part, I would say, is the application in highly automated manufacturing. So I did here a review of production planning of a body shop and collected a lot of primary data in collaboration with the AREAS project again and with the University of California. And then I integrated these two approaches here and developed at the end an algorithm which can somehow derives life cycle targets for the body shop. So the question 1 I would like to answer now is how can sustainability assessed in automotive manufacturing using the concept of target states? For me, it was always quite important to work with industry. So of course, we had the key partners here of the AREAS project, which were KUKA, Daimler, and Siemens. But along the way, I had the opportunity to talk about my approach with Tesla in California, with Danfoss as one of the partners in AREAS as well, but they were not really into car manufacturing. And then with Volkswagen, and yeah, so they were pretty helpful. So I could mirror my approach and see if it's a good approach, applicable approach, because I wanted to develop an assessment method which can be applied in actual manufacturing environment and not just another method for the drawer. So that was my idea. And based on this collaboration, I was able to derive objectives for the new sustainability assessment framework. And in total, I have derived 4 objectives. So the new framework should have addressed the full scope of sustainable manufacturing. That means we should relate the impact of the product to the production development. Then it should reflect global targets, like the planetary boundaries concept, which somehow describes the carrying capacity of the Earth. So how much we can actually still emit. Then we sustainability should be understood as a relation between 3 factors: the demand from the customers, the so-called functionality, the product and the production system, but it has to take the life cycle perspective always into consideration. And then it should be able to integrate target states to the very last production station. And the second part about the background of the new framework is the derived requirements from industry. So it should be aligned to the existing decision-making process. It should fit to the existing product and production planning processes. So it has to be a top-down approach. Then it has to be transparent so that all involved managers know what kind of target they should use. Then it should incorporate the life cycle approach, because the latest ISO 40001 said that the life cycle approach should be considered. And then we have, of course, which is quite important for car manufacturers, not really, they don't really want to have additional workload, and it should be built up on existing software. There are a lot of product lifecycle management softwares available, and the framework should be integratable to this one. And cost-benefit ratio is kind of obvious for car manufacturers. And yeah, so the result is the so-called sustainability cone. And if you remember that we should integrate the demand from the customers in this new framework, we're going to start here with a small customer. So, and you are asking for mobility, for example, as a function, or transportation. This transportation has to be defined. So the functional unit has to be defined. The functional unit is quite important in life cycle assessment. So all the results are going to relate to this functional unit. And for example, a functional unit can be 200,000 kilometers of individual transportation over 10 years. And this can be provided, of course, by a car, or maybe by an electrified car. And if we now integrate the life cycle concept, we can assess the environmental impact, which is represented here with the CO2 equivalence. You can see that a car emits roughly 38 tons over the life cycle. This number is based on 20 analyses, which were conducted from Volkswagen, Ford, Daimler, and so forth. And that's the median of it. And the manufacturing stage contributes roughly 6.7 tons to the overall emissions. The use phase, 31 tons, and end of life, 0. Because most of the car manufacturers are taking the conservative approach, because they are quite unsure how many emissions can be saved during the end-of-life phase or will be emitted. So most of the companies are saying, okay, we say 0 at this point. But the question is, how much is actually caused by the production system? And if we remember, we would like to introduce these numbers in the planning phase. So how should you know how many emissions are produced or caused in the emission in the planning phase? And if we go through here, the car body will be produced in a body shop. And the body shop consists of several sublines, like the underbody line or the side member line. And then you have a lot of different technologies to join actually the different parts. And at the end, there are a lot of robots in this car body production. To visualize all these, I've developed the so-called sustainability cone, which represents here the functionality, the functional unit as the first level, and everything is related to the functional unit. And these arrows indicates the life cycle on each stage. On the far top, it's the product specifications, and here down here the production parameters, and from the top down to the lowest level, there are a lot of decision making happening. This is the backbone of my thesis, so I try to visualize the interdependencies between the customer and the robot. But there's still a problem how we can, a methodological, a challenge actually, how can we solve the barrier here between the module and the system, because here we are assessing a unit of product, and here we are assessing the production of one unit. It's a methodological problem which I would like to solve later on. So the intermediate, or the outcome of the method development is that the sustainability cone has been designed for industry. So it incorporates existing stage gate model, represents the existing top-down decision-making approach, and it actually reflects the iterative and overlapping product and production planning. So if some products are changing, you can go level up and decide how to adjust the carbon budget. And then it embraces the target state concept, so absolute targets can be implemented, and it's able to visualize potential sub-optimizations between the different levels. The feasibility and applicability in manufacturing must be tested, which I will do in the next slides. So the combination between with production simulation has to be tested. The integration of life cycle assessment according to ISO 44 as well, 4040, and the available data in manufacturing planning has to be tested, or we have to find out if there's enough data available at this point. So the second part is about the integration in current assessment methods. So how can we merge life cycle assessment and production simulation to avoid sub-optimization? So the sustainability cone again, with the product-related specifications up here. And if we look into detail, we can see the life cycle here. So the raw material production of the different components of the car, the actual production in the facility, the use, and the end of life of the car. But if we want to combine it now with the production parameters, we have the problem that we have two interfering life cycles. So the question is, how can we overcome this barrier in a systematic and applicable way? And I would like to exemplify this at a quite easy example. So if we're looking now at the process, which is consists of a welding step, a clinching step, and a laser production step. And based on this process, we are producing one car body. It's quite easy to generate the results for this, right? For one functional unit, production of one car body. We can collect all the kilowatt hours along this way and assign this to a product. That's quite handy. But if we look now to all the other components, like the factory itself, with maybe some lighting, some photovoltaics on the roof, some windmills somewhere on the side, how should we assign this to this car body? So the idea is that we somehow divide all this carbon footprints and align this to the functional unit. And of course, there's another major impact. It's the machinery. If we think about the complex production of car manufacturing, we have a lot of machinery in there, and there's a lot of environmental impact. And we have to consider this as well and align this to the functional unit. And how can we do that in a handy, applicable, and feasible way? That is what we did with the new holistic and applicable assessment method. We've developed this with the TU Brunswick together. If anyone is interested in manufacturing simulation, you should go there. It's a pretty good group. And we started with the idea that we want to combine manufacturing simulation as the driving force, because the industry is always looking for improvements in the manufacturing, in the actual production line. And we said, okay, that is the driving force right here. So we're going to simulate the manufacturing system, and we will get some energy data out of it. But if we remember the whole factory picture from the slide before, we have to add machine tools and equipment as well, and HVAC and lighting to get the full picture. And that is why we use the life cycle assessment approach. So we defined the goal and scope, and this is more or less the life cycle model. The next part was the next part of a life cycle assessment is to have a life cycle inventory. And how did we do this? We defined some parameters which somehow pull all the information based on the predefined functional unit out of databases. So, for example, if we have one photovoltaic unit on the roof, the actual CO2 emissions are stored here in this database, like EcoInvent or Gabi. And then the manufacturing simulation says, okay, I need this specific share of 1 unit of solar panel. And then we have assigned it to this. And this happens with all the other machinery as well, depending, of course, on dynamic aspects and so forth. But this is it would be a whole other presentation if we talk about this. And at the end, we have to add, the result of this is actually a material flow analysis, so an inventory, and we can assign the environmental impact assessment at the end, and by using a midpoint assessment method, which is based on CML. And yeah, by this, we were able to assess 5 different impact categories for these kind of manufacturing systems. So, and at the end, of course, there's an interpretation if it makes any sense, these results. And yeah, the outcome, I would say, for merging these two approaches is that the challenge of 2 interfering life cycles is solved by using the functional unit approach, assigning everything to the functional unit. But it requires substantial knowledge of the process because everything is manual so far. It's not automatized, and we haven't integrated it into PLM systems and so forth. And we can say that production-driven assessments are possible. And we can basically avoid sub-optimization between manufacturing, overhead, and the process. So we have the full picture and can see the different shares and see, so different shares for machinery and infrastructure, direct energy consumption, or indirect energy. Yeah, and I would say it's possible to have now a holistic assessment, and this actually leads to more effective solutions, which I think is quite important because efficiency improvements in manufacturing not always lead to effective solutions. So if you, for example, integrate renewable energies into the production system, you need storage systems, for example, which have additional environmental impact. And by this approach, we can see the whole picture and say, okay, effective or efficient solutions are not always effective. And the third one is now the most interesting part, I would say. It's about the application in highly automated manufacturing. And we have to answer, or I would like to answer 2 questions here. So how can a target state for a production be integrated in the early phase of production planning? So we would like to understand how it works, the production planning in car manufacturing. And the 4th question is how we can integrate target states and assign them to individual processes. So we can use life cycle target setting in production planning. And to understand the case I will present later on, I would like to focus now on this area. So the car body will now be the case, and the car body is produced in a body shop, like I said before, with an underbody line, spot welding, and robot. And if we assign now a life cycle target here to the car body, or I would call it from now on life cycle target because it includes the whole life cycle of the car body. What does it mean for the robot XY at the end of the line? So how can we allocate this in a transparent and consistent way? So if we look now at a typical stage gate model in car production, we can see here the whole flow, more or less, the strategy development here, and the start of production up here. And in general, I would say it takes roughly 60 months from product concept to the start of production. But of course, they would like to shorten it now. And it's maybe 4 years now. But just to understand, first of all, there's a strategy development. So what kind of car do we need for the different market? What are the customers are demanding? What kind of car? So SUV is a huge topic now. So they're producing all the utility vehicles. And the next step would be the product concept. So that is what you see at all the different car fairs in Frankfurt and so forth. There are a lot of nice concepts. And then actually the production planning takes place. And so between the 16th and the 46th month before the start of production. So that is where I would like to implement my allocation method. This is a little bit wrong here. I should move this to month 46. I'm sorry about that. But to understand the production of a car, I would like to show you this graph. And usually the production starts in a press shop, then the body is produced, then it moves to the paint shop, then the powertrain will be attached, and then the final assembly. These are the 5 steps. But I will focus on the body shop because it is the second biggest energy consumer in car production after the paint shop. But there's a lot of infrastructure which is used. So if we think about all the robots in there and so forth, they need a lot of area. If you go to a car manufacturing facility, there are robots everywhere, more or less. And on the other hand, the body shop is one of the key competences still from the car manufacturers. So they are producing their actually car. So they are not giving that to external partners and so forth. They're still producing that by themselves. So that is why I choose actually the body shop. And of course, I could collect a lot of data in the Areas project. If we look now to in a body shop, it's usually separated in 3 different lines. So the underbody structure, the assembly, where the underbody is joined with the roof and the upper back. And at the end, the doors and the fenders are attached. To give you an overview how this actually looks like, we can say that in general, 500 different parts are joined along this process here. Up to 500 cars can be produced in this kind of line. But I would say it's between 250 and 500,000. The cycle time ranges between 40 and 60 seconds. So every 60 seconds, a new car body is coming out of this line. The degree of automation is 98%. So yeah, and the availability has to be higher than 95%. If we talk about primary energy consumption, we can say that 50% is due to the movements of robots and 50% for other consumers. If we now look at the robots, we can say that in total 1,200 robots are installed in this line, and it's increasing. So the last, if we look at the International Federation of Robotics, they said that 6 years ago there were an average 700 robots installed. So every product cycle there will be more robots. I don't know where the end is, but 1,000 robots is a lot. And if we think about that a robot has a similar carbon footprint like a car, it's huge. It's a huge impact. And so the average energy consumption per robot is 4,500 kilowatt hours per year. It's roughly 1.5 households, I would say, just to get an idea how much it is. But it only works 90% of the overall time. The reason for that is the organization of the production line to secure the highest availability. If you look here at the core line, zone 1, which is working almost 24/7. So the robots are working all the time. And so there's a lot of energy consumption here. We can have a look here now at zone 2, where medium parts are joined to larger parts. So they are actually providing all the time products to zone 1. Then we have a logistics area around here. So some products are coming from external sources and so forth, and they have to be integrated here. And then we have the small parts around here, where most of the employees are actually still working. So they are providing, I know, a small metal sheet to process with their hands. So we can say that the activity level decreases from zone 1 to zone 3. And in average, only 90% of the time the robots are working. But if we're thinking about here, it's almost 100%. And this is how it would look like in real world. Here in the middle, you can see the high robot density. So that is zone 1, the core line. Then we have the zone 2, which actually provides some parts. And then we have the zone 3, where you can see some low-cost automation, which are called in the data sheets from the car manufacturers LCA. So there was a huge confusion when we made the first workshops. We're going to talk about LCA. And then we started with life cycle thinking, so no one knew what we are talking about because they expected we're going to talk about low-cost automation. So that was quite funny at Daimler. Anyway, we can say a lot of infrastructure, machinery, and area is needed. You can see it here. And yeah, but for my carbon budget allocation, I need, of course, some data. And that is what I would like to talk about now. So the OEMs, the car manufacturers, have a general layout between the 16th and 46th month available. So I'm getting this kind of overview. And they're actually saying what kind of intermediate products are handled in this line. And then they describe the general product flow. So how are they going to join all the different components here. So the joining sequence will be described. You can see here some numbers, for example, the cycle time of 45 seconds. And yeah, so I have to extract these numbers somehow to get my allocation method. But there's more information available if we are looking more into detail. They even describe the different subcells here. And they say what kind of components are used in this area. So Modul Rob Punktschweißen means robot spot welding. This is maybe this one. And then we have a table, which is this one. And yeah, so I'm getting a lot of information what kind of machinery is used. And in total, I was able to identify 34 different joining and handling technologies like welding, adhesive bonding, laser, and clinching. And then 61 different components were identified, like tables, turning machines. But there was no weight assessed to the different components, no space or required space they need, or installed capacity, how much electricity they will use. So I had to look up all this in the different product sheets and yeah, assigned all this information to the different components here. The next part is, or the idea was actually to develop a method which is applicable to product lifecycle management tools, simulation tools, to increase the applicability. And in these software tools, it's usually separated. The information is usually separated into 3 parts: product, process, and resource related. And I wanted to assign my data, which I've collected in the data sheets, to those. So product related, I have the number of parts which I handled in this process. Then I have the weight of the different products and the dimension. And the process as well, where I have process data as well, the cycle time, the joining sequence, and the joining equivalent. The joining equivalent is kind of key for my assessment because it compares 2 different joining technologies based on a specific number. If we look at spot welding with a specific stiffness for one spot, and we want to use another technology like laser, how much of laser do we need to get the same stiffness? So the car manufacturers invented their own equivalents, and for laser, for example, it's that we need 10 millimeters of laser to achieve the same stiffness like one spot weld. So it's possible to compare different technologies. If we talk about now resource-related data, we have the technology. Two different kinds are used, joining and handling. And then we have the components, like tables, fans, and so forth. And we have the employee, which I mentioned here in this data sheets as well. Yeah. And then I said, okay, how can we describe actually the new allocation method? And I said, yeah, somehow all the data describes the activity of the different lines. So I called it activity-based allocation, a top-down approach. So because I'm getting the data from the whole line, and then further down, it's a subline, so I'd call it a top-down approach. The allocation method integrates a typical production line structure, so line 1 to 3, and so all subordinated levels. It defines factors for product, process, and resource-related activity, and it's more or less compatible with PLM system architecture because of the clustering. It represents the stage gate model, so it's somehow I use all the data from between the month 60 and 46, and I'm only extracting data which already exist, and it's an automatic extraction. In a huge Excel sheet, I put all the information, and then I have to press the button, and all the information is getting out. And it's applicable due to the similarity to cost target setting. If we think about how a car is planned, you always have a financial budget on the top, and then it will be allocated to the different lines or to the different managers. So my kind of thinking is almost the same. And it's able to define process, overhead, and infrastructure targets. And it encompasses life cycle assessment. But this is a lot of talking now, so I would like to use all this information here in this case study. It's a quite easy one. So if we look at line 1, which I've shown you before with the zone 1 and zone 2, and the line 2, which looks quite different. And we say, okay, we have a carbon budget now available, and would like to somehow split it. So how much of the target stage should be assigned to each of them in the planning phase? So to know if the product line developer is in the right direction to fulfill the target state. So that's the question. And can the available data be combined to arrive in profound allocation factor? These are the main questions. And now it's getting a bit cryptical, but I hope you're fine with it. And so if we look at this formula here, it describes somehow the product activity. So you're looking at the different number of products in line 1, which I handled here, so the product flow, and line 2 with 3 numbers as well. If you're wondering what TLL means, it's a technology readiness level, which I used in this approach as well, because some lines are well developed, it's quite mature, so it has a low uncertainty. So it's getting a 9. If it's a high uncertainty, it's only getting a 1. So we have a lot of additional planning to do. So we have 3 different products which I handled in each of the lines. The mass of the different products is here 120 kilograms and 250 kilograms in line 2. The dimensions are similar. And then at the end, if we're putting all the numbers in here, we can say that the product activity factor is 1.32 in line 1 and 1.68 in line 2. Yeah. We can do this with the process as well. I don't want to get into detail, but I have considered the cycle time here, the joining equivalence, and the joining sequence. So how many steps are necessary along this production line. And we can see that the process activity is higher in line 1 compared to line 2. Resource related is a bit more complicated, but it's because we have to consider energy consumption and so forth as well. But in general, it's the same approach. So we looked at the involved technology, involved components, and the employees. The employees are treated equally to technologies. So that's the idea that one robot equals one human. And at the end, we have a resource activity allocation factor of 1.3 for unit 1 and 1.6 for line 2. And yeah, but we need an additional factor to somehow consider the resource intensity. So I've looked at the different weights of the different technologies here. So I identified that the weight of the machinery is 32 tons in line 1 and 43 tons in line 2. In total, they consume 250 cubic meters compared to 335 cubic meters in line 2. And line 1 consumes 1 megawatt hour compared to 1.3 megawatt hours. So technology activity is allocated with 1.3 to line 1 and 1.7 to line 2. So I can say, I'm happy to say, that for each cluster line cell, an individual activity-based factor can be derived. Now we have to combine these three factors. So just to remember, these are the different factors. And then we have to add them and divide it by 9 because they are treated equally. So I was not able to say that the product is more important than the process or the resource is more important than the production parameters. Of course, we can change this later on, but it's not up to me. It's more to the internal effects of the car manufacturers. So we are having now the life cycle target for both lines, and then we apply this allocation factor here. And we can say, okay, line 1 is getting 149.5 of the carbon budget, and line 2 155.6. So for each line, subline cell, an activity-based target is assigned based on all the planning data we have. 40 seconds. Okay. And if we look now at the sustainability cone again and apply all this thinking to the whole chain which I presented before, right? We started with 3.1 tons of CO2 equivalents. Sorry about the missing CO2 equivalents here. We can allocate based on different data the different flows here, but we always have to follow now the blue one, right? I don't want to get into detail. Maybe we have the opportunity later on to talk about this. But now we talk about the production itself. And if we look at the system and line, we have the 305.2 kilograms, which I presented before. And based on all the information, I assigned here another target because it's a different line. And I've split them a lot here. But the idea is I want to get even a level further down. So we're here now on line level, then technology is down here with 3.2 kilograms, and the technology is basically spot welding. So I was able to derive different targets here. Some are attached to stationary production, and some are attached to robots. So I was able to derive different targets here as well. But at the end, I was able to derive the life cycle target of a robot. And it's quite consistent because I'm always using the same data which is available at this planning stage. And if we compare these results, these are top-down results, right? I used all the planning data. But if we compare those with the bottom-up results from our Areas project or another Audi study, we can say that my results are quite quite good because it's 3.9 grams for material in production, and the life cycle assessment from Arias and Audi says it should be between 3.6 to 5.6 grams of CO2 equivalents per functional unit. And the use I've here is 24.6, and they say it's 26 to 27. But the reason might be that I assumed another cycle time, and the movement was a little bit different, maybe. But I would say, in general, I'm getting into the right direction. Now I would like to conclude and do some recommendations. And the conclusion one is that about method development. I would say the framework has been designed along existing stage gate model. So represent actually the car manufacturers, combines the demand from customers with the product and production, and it supports effective planning in an applicable and consistent way. And it visualizes actually all the different interdependencies on several levels and includes the life cycle approach. The integration in current assessment methods, due to the combination of manufacturing simulation and life cycle assessment, we were able to achieve a holistic simulation of manufacturing systems, and we actually used the functional unit to overcome the barrier between product and production. And we were able to integrate dynamic manufacturing effects like provision of renewable energies depending on the time in the day. And we were able to individualize the life cycle assessment, so we can provide product-specific life cycle assessment results. Conclusion 2 is the application in highly automated manufacturing. So the target states, the 2 degrees target can be broken down now in the early stage of production planning. And we can assign targets to the individual processes. And it's based on typical available data in the automotive companies at a very early stage. And we can integrate the algorithm into existing planning tools. So I at least try to provide all the information according to the PLM system structure. And it enables managers, product and production planners to keep focus on effective solutions, not just focusing on efficiency improvements in their specific field. And it allows decisions to be analyzed holistically and thus address potential trade-offs. Limitations are always there. And of course, I always needed more time and more case studies and so forth, but I'm quite happy. But anyway, the goal was to develop an applicable method. However, there was limited data. So I always ask for more data from the car manufacturers, but they are not so easy, I would say, with data sharing. So I'm quite happy that I get some data from the Arias project. The approach is only based on Arias, like I said before, and the support of 2 further OEMs. So I explained how I did that, and they said, okay, that sounds reasonable. Okay, we can do this and so forth. And yeah, so I'm not completely, I've not developed the method in the complete wrong direction. The focus was on European circumstances, and I've developed it only along the body-wide production. Maybe the approach doesn't work really for the paint shop, but yeah, that's might be another topic. And the combination of life cycle assessment and manufacturing simulation was tested manually, and yeah, and the actual implementation in a production development process is missing. We actually tried that with Delmia, with one of the partners, but yeah, there was a lack of time, so we not did that. And one of the drawbacks is actually that, or disadvantages is that I only focused on global warming potential and primary energy demand because of the missing time and of course of lack of data from the industry. And yeah, and I can say that that the burden shifting between different impact categories cannot be excluded by my category, only between global warming potential and primary energy demand. further development, I would like to integrate it into manufacturing planning software to increase applicability, limit the time effort, and other impact categories I would like to look at. But it needs additional data from the car manufacturers. So we should set up a project, an industry project with different car manufacturers. And I would like to combine those with those new data with the algorithm and adjust the algorithm accordingly. And I would like to improve or minimize the sub-optimization between impact categories. And it could be tested in other parts, like I've mentioned before, in the paint shop, for example, and identify if this kind of thinking is applicable to other sectors and develop a sector-specific allocation factor. That's it. Thanks a lot, and I'm happy to receive some questions.